Johnny. We'll start with how this course runs, and it's with respect to other course, and then we'll give you a helicopter view of machine learning, and on the technical level, what this course covers roughly, and what it doesn't cover. Let's get started. So people were wondering where the notes are. They're on Piazza under resources page. There's this whole section called lecture notes. So they will go there. We will not use Wattle except for exams and quizzes in general. Yes, okay, somebody else already answered. So I'm basically monitoring the video feed and I will not see questions in Teams in real time, but I will pause a few times for questions. So at that time, I will look at the chat and you guys feel free to unmute and ask me. So where we are, as many of you know, is in the middle of the, let's say, sequence of machine learning courses in CS. Here are a picture of AI and machine learning related courses. About 3/4 of this class have taken intro to machine learning using the mathematics for machine learning textbook. A quarter of you haven't. So in this class, we're going to build on intro to machine learning more tightly than the previous offers of this class. Well, if you haven't taken previous editions, it's kind of irrelevant, but it's relevant for some of how the assignments are structured and expectations, which also means that in the course, a lot of you would have seen the course schedule table on the website. It will require you to pre-read some of the MML material if you haven't taken IML. All right, so the focus of this course is mathematical thinking in machine learning. The rational derivation of implementation of a broad set of models. And in-depth appreciation and critiques of models is the emphasis. After this class, or some of you already have taken AML, Advanced ML, which talks about convex normalization and a couple of other approaches. They are more focused on subsets of machine learning. So arguably, this class still basically does the breadth first view that covers a diverse number of approaches and models. So after this class, or concurrently, you could take, for example, document analysis that's offered in the second semester, focusing on NLP and other things, optimization. Some of you are taking computer vision concurrently and so on. There's a related thread on AI and advanced AI. The reason I mentioned here is that things like reinforcement learning, POMDP, so partially observed market decision processes are covered there currently, and it's offered in the second semester. This is roughly who will be teaching you different parts of this course over the semester. There's myself and a team of 12 confirmed tutors. We're in the process of recruiting 1 or 2 more. You will get to meet them. For those of you who haven't, who want to know a little more about them, you can look at the introduction videos that we post on YouTube and streams. Feel free to let us know what you think. A few more of those videos will probably go up during the rest of this week. So this is the videos, and the content is basically roughly a few words about who the tutors are, what's their favorite machine learning algorithm, their advice for studying this class, because the vast majority of them have had a long experience with machine learning, either tutoring, studying, or doing research on it. And also, in general, what are the misconceptions of machine learning, big picture challenges with machine learning, and so on. A few words about logistics. So still slightly less than half, but a significant portion, about 45% of this class is over, it's not in this time zone. Not sure if they're overseas or not, because Perth is in like 3 hours behind. So which means we have to cater to both the remote and local student cohort. And with the current mask mandate still in place, plan to hold most of these sessions, which we call online lectures, still online. They're recorded. Tutorials and labs are not recorded. Some will probably be in person. We are having a tutor meeting this afternoon, right after this, to talk about it. If tutors are comfortable and safety measures are in place, we'll try and hold them in person. So as for myself, I plan to hold probably 1 or 2 lecture sessions in person, and we'll figure out the dual delivery option a bit later. So in the schedule, there is still, there's tentatively 1 placeholder for that. We might add 1 in the second half of the semester, because I do have a strong desire to meet some of you in person. So we'll see. Fingers crossed that can happen, pandemic permitting. I know we're all sort of very tired and exhausted with this online learning thing, but let's just try and make the best of our time together this semester. And we'll keep you posted. Most of you probably have figured out where things are. I'm not going to go through them again. And I would just like to say that the significant clash with engineering data analytics is noted, and student services is working on it. Basically, this is a required class for about 160 of our current students. And also this class is currently at, enrollment is at 290. It's about 50% bigger than what we have ever. So this has challenges, so please be patient of each other. So for the MML CV students, the clash might be resolved, and for the rest of you, this class may be moved to a block 2 hours earlier. So I know that it's likely that it will incur some new conflicts, but I trust student services to sort of look through everything and try and do the best for everyone. One word about learning. Yes, of course, machine learning is done by you. We're here only to help. Lectures such as this is one of the resources that help. I know that in the current day and age, even if we are doing this in person, a lot of you will choose to do something else in that lecture slot. Same with online videos, that's fine. I hope you will find the small group, like tutorial sessions, very interactive and useful. And also most of the programming content is covered in tutorials and assignments. We might ask some questions in the exam. Last year we did not, but this year we might. But the programming content is not in lectures. Let's say I won't talk about Python code. That means one of the advice that multiple tutors give in these intro videos were that programming are important. So get your hands a bit dirty in order to thoroughly understand something, and also start early. And they mean it. So the estimated time that I will be talking to you twice a week is about, I would say the expectation of that, the mean is about 1.5 hours. There were a few sessions that are longer. There are some sessions that are shorter. I'm not going to try and use all like the 2 hours. That's probably just too long for you to sit through. And I also know that, like, for example, an hour and a half long video is not ideal for someone to consume offline. At this point, I think I trust you to sort of scroll through enough using slides as anchors, because you have them. Tutorial sign up is a hot topic, so it will open once we have the additional, well, basically the course schedule confirmed, the swapped lectures and additional tutorial slots. And we'll try to fit everybody in. Assessment items is what people care about. So I'm just going to say there are 2 bigger assignments, one due in first half of semester. The second one is, I think, due in week 10 or 11. They can be submitted in pairs. People can choose to team up with another student or do it themselves. here are this writing, and the webpage spells out some expectations. There will be, in addition, some video assignment to basically get you to talk about a technical concept in 4 to 8 minutes. That will be graded. Last year, we've received many great inputs for the video assignment. We look forward to the cohort this year. There will be 2 online quiz. Last year, there were only 1. So again, 1 in each half of the semester to help you sort of warm up and like practice some of the content and get some instant feedback as well. Exam will still be online, the last I heard, on Warthog. We assume you already know some probability, linear algebra, and comfortable manipulating them. We also assume you already know or can program in Python with a bit of pickup. So the practices for these are basically exam. What's called exam 0 is essentially a self-assessment. So you should look through it, try and do it, try to spend an hour or 2 or 3. Hopefully it's doable in 3 hours. And then in this one, there is what's called tutorial 0 that has a Python notebook and NumPy warm-up, as well as manipulating matrices. Yeah, exam 0 is a hurdle, but we expect you to impose it on yourself. If you feel that it's just too difficult and you haven't taken the prereq, maybe wait a semester and take the IML first. Yep. And we'll release the solution to the former later on. So one more about the textbook. We will be still using pattern recognition and machine learning by Bishop. This textbook was written in 2006. But it has, I feel, compared to many other books, including, for example, the new Kevin Murphy book, it's carefully written pedagogically. It's not aiming for covering everything, and we will occasionally refer to other books. It has a lot of timeless material. Some of the material, the approach is still valid, but not as widely used, and we will selectively not cover things. And the book has a lot more material than we can cover in 1 semester anyway. So I myself find it a nice read. So this is, again, one of your resources. You could, for example, use this in the lecture slides, like together, which may mean that you can use those to understand the material. If you wanted for example, 1.5-hour guided tour, then come to this Teams meeting or video. Then you'll get to hear my rendering and interpretation of it. One word about the problem sets in the book. Some of them are listed in the top of the tutorial sheets. Most of the problem sets in this book are meant to complete the book content. Basically, there's a gap in derivation and something and it's left as a tutorial exercise question. I think if you attempt them and you can do all of them, that's great. But it's not super similar to the kind of exam questions you will encounter because it's likely going to take more time. And it's assessing slightly different things. So about so there's a number of books that we'll be referring to. These are the 2 main ones: Mathematics for Machine Learning. So this is the book used in IML. It's well written. It actually has lots of influence. It's a much newer book, right? It has had lots of influence from the PRML, or main textbook. So if you're familiar with MML, you should find PRML like a reasonable read in terms of notations and style. But there are notable differences. The MML book tend to spell out all derivations and math, but SML sort of is more parsimonious in that sense, and sometimes we need to fill things in. Kevin Murphy's machine learning book, both the old and new version are great. There's also the information theory and machine learning book. I'm not listed here, but I will refer to it maybe time to time. So, I would like to borrow this blurb in the preface of the ML book to say where this class is positioned, especially if you're new to machine learning. So machine learning is used widely these days, and the starting point for a lot of people and people using machine learning in practice is probably the one in analogous to music is what's called astute listener, right? You have your musical taste, you can play, you can focus. For machine learning, you can use cloud-based tools to plug and play, connect your data flow to machine learning, focus on extracting insights, critique the correctness and outcome, interpret the results, and so on. The next level is experienced artists, understand machine learning interfaces, their uses, and limits. One could argue that many other classes on offer are at this level. For example, the famous Andrew Ng's online machine learning class gets you a start towards it. It's sort of a quick intro. It only stops at, I think, SVM and linear classification and regression, but it's in that positioning. So, and then the next level is fledgling composer. Basically, you develop the skills to extend existing algorithms, to see the connection and distinction between different algorithms, rather than seeing different algorithms and models as a separate, like islands. So this gives you a foundation, for example, to tweak and adapt machine learning models for a particular problem, derive new problems, or do research. So I would say statistical machine learning is positioned in between the second and third. There are a lot of advanced content that could go towards like this fledgling composer analogy that this course is not able to cover. I hope you find this classification helpful in some way, or maybe in hindsight, after this class, you look back at these 3 classes and you can grade yourself on it. Finally, a word about class reps. So this is a large class with somewhat challenging content. I guess the student body will have voices and opinions that you might just want the school or us to hear. If so, I guess volunteer to be a class rep. I think at a minimum, we will look for at least 1 class rep each in the 4670 cohort and the 8600 cohort. If you want to be one, you can write to student services or write to me, and we can set this up. Thanks. Any questions so far about this part? We're done covering the logistics pretty much.
Yeah, I actually do have a question about the assessment. So I'm just wondering whether, because the assessment can be done by 2 people or 1, right? So I'm just wondering whether the marking rubric is going to be the same for both?
Good question. Yes, it is the same for both.
All right, cool. Thank you.
Yes, drop-in sessions. Right now, there are tutorials sort of almost everywhere on the schedule. Especially if the tutorial is online, I feel like you can use that as a drop-in session. My drop-in session is after the lecture. On the schedule, there's 2 hours, and you can use the remaining, like the time towards 4 o'clock, for example, in this slot as drop-in session. If you need more than that, shoot us a note. Depending on, I guess, demand and interest, we might set up additional drop-in sessions. But essentially with tutorials like almost going on all the time, my sense is it's not clearly needed at this point. But of course, towards major deadlines, we probably will have drop-in sessions for people on campus, but also just post a PFSI message, like if you would like that, right? We will also want to gauge the demand. Is there another question? I think my scrolling is not working so well. I think there was. All right, lab sign up has not opened. because we're waiting for the course schedule to settle, and we will post a Piazza message as soon as we open it. Hopefully that answer is good enough. I know everyone is eager to pin down their schedule, and this is very high on our priority list as well. Okay. Okay, so we get that nailed in about half an hour. Yes, so we intend for the Piazza resource page to be the place we post files, if we do need to post files. Yes, exam 0 is there. The programming and part and data also there. The tutorial 0 is also there. Thanks, people, for answering. So here is in the next maybe 40 minutes or so, we're going to talk about this helicopter view of machine learning. It's just one of the views. It's probably a little bit different from what you heard from IML and their classes. So let's get started. And after that, you're welcome to ask a lot more other questions. One of the most common, I would say, hyper misconception about ML these days is that it's being equated to artificial intelligence. And moreover, deep learning is also being equated to machine learning in the, I guess, popular perception, which is not true. So let's try and first define machine learning. We credit the first definition, the definitions, and I particularly like two of them. The first one is by Arthur Samuel in 1959. It says machine learning is the field of study that gives the computer the ability to learn without being explicitly programmed. So being in this class, I'm sure you know what being programmed means. And for example, in Comp 1100 or the like first year kind of classes where you're programming the computer to say solve a puzzle or play a game, where every step is essentially predetermined. In here, the computer are learning from experiences or data rather than being told what to do. It's so Arthur Samuel proposed this in a paper about using how to teach computers to play checkers. So checkers is this very interesting game that has a significant position in the history of machine learning. It's featured in Arthur Samuel's first paper. It's also the first game to be solved by a reinforcement learning agent done by Gary Tusharo of IBM way back when, using a neural network, using a non-deep neural network. Right. The second definition is a bit more specific. It's done by Tom Mitchell, one of the more recent pioneers. He's at CMU. It says a computer program is said to learn from experience E with respect to some class of task T. So this gets a lot more concrete about what the computer is learning. And it tries to achieve a performance measure P. If its performance in the task improves with experience E, then it's set to have learned something. Right. So as like most of you by now knows by taking IML or reading, this is not equivalent to thinking or intelligence at all. Right. In the checker example, the experience is the games played by the program, and the performance measure is whether, for example, the program wins or not. So of course, for games, just having the binary outcome of win and lose at the very end of the game may not be enough of a learning signal to essentially adjust all of the different steps in the whole game. That's where basically, for example, estimating future reward and the whole reinforcement learning strategies kicks in, right? And in this particular case, the game played by machines and humans are called data. And which is interesting. So in terms of this history of machine learning, since we claim that it started in the late 1950s, in the 1960s, computer still learns mostly from data using rules, right? So this is symbolic AI, which are still largely at play for solving problems like university scheduling and other planning tasks. Perceptron, which we will cover in this class for historical interest. In the 1980s, it turns to artificial neural networks. In the 90s and 2000s, statistics has been playing a larger role in machine learning. And the reason, right? So the reason we look at this historical node is that the time when statistics kicks into play a large role coincides with faster computers with larger storage capacity and better ways to compute. And there are more interesting algorithms and larger amount of data available. So all of these sounds familiar, right? We just swap in a few keywords. We can then describe basically the recent advance of machine learning with even faster computers and parallel computation, GPUs, larger hard drives, and not just memory, and also memory and programming approaches and so on. So as one can see, maybe we have seen, well, we're machine learners, we learn from experience. So at least there are two experiences that shows us there has been large leaps in this field due to these factors. And one wonders when is the third and what would that be? Well, in order to, I guess, participate in the future of machine learning, let's first look at what the current machine learning looks like. Here is a simplistic view, right? Based on task divisions. There are many ways to divvy up machine learning. I'll give you a glimpse about the complexity around the end. But for now, let's assume there is supervised learning, classification or regression, where we know there's a target, there's some data learned that target. Unsupervised learning, there's no target, here's some data derived, some patterns based on a particular desired objective. And reinforcement learning, which we won't cover a lot, but we'll say one word about it a bit later. And in reality, they are all sort of, there's lots of gray scale or in between these bigger buckets. We can view each of these large classes of learning tasks as sets of tools and methods that can be combined, used together and adapted and used to define new tasks. And this is what this class, after learning class, this class you have practices and the language and the tools to do so. There are still a fair number of you who are new to machine learning. Let's just look at one simple example that is very concrete to illustrate what some of these tasks are and what we cover, right? So this task is, let's say, predict the price of a somewhat complex object, such as a house, rental price, or like, selling price, right? If you have been living in Canberra for a while, you will know this website called All Homes. Basically, all the real estate ad goes there. You look at it, oh, there's the location, size, features of the house, and usually the price is hidden when it's on sale, which is really annoying. If you were on the market, you will want to do it the data scientist way, saying, oh, can I have some of an estimate of the price so that I can narrow things down, right? So this we can treat as a supervised learning task because in the real estate market, the past transactions are all recorded. They're not publicly available, but the data, like if, there are firms who sell this data. Assume that's available, then we essentially have a data set that contains n examples, right? Where the x's, let's say we look at the simplest feature first. The x's are the input and the y's are the output, namely price. maybe let's look at the size of the property in square feet as the first feature. And if we graph them on a 2D plot, we might see like this, they lie somehow on a slanted straight line-ish, right? So from these data points, we given a new data point, say we haven't seen houses that are exactly 800 square feet, but what would the price be? So from this, like if from just learning by eyeballing, we can probably guess the price range will be in this neighborhood, but not here, right? Which is kind of obvious. And the question is then, how do you mathematically express it? So the task here, describe machine learning by task, experience, and metric, is basically if given a residence has X square feet, predict its price Y. So the simplest hypothesis we could express on this is, oh, it might be a line or it might be a quadratic curve. And that will be covered in essentially the rest of this week and next week, regression tasks. So you say, well, the square footage of the building itself is too naive. There are many other features that describe the, let's say, price feature correlation. For example, the size of the land. Of course, right? So if you add one more feature, then geometrically you could put the two features in the output on the 3D plot. And now our data set will become X is a vector that decomposes into X1, X2, and the supervision we give it, it's called supervised learning, are the historical prices of each house. And we're still doing the same task. Given a new X1 and X2 pair, try to predict its price. All right. Let me pause. I think I saw a few questions coming in on here now. My computer is really slow. Right. So indeed, the term learning, or for computers to learn to program itself, is implicit in our current right. So in the machine learning terminology, the program that's generated from different experiences or different data sets, the code itself does not change, but what's called a model file, or the coefficients, if we're doing regression as in what this page suggests, does change. And that corresponds to different decision rules, right? For example, you say, oh, if these features add up to more than 100, then predict it rains. If they don't add up to more than 100, then predict it won't rain. So that's certainly different program, like rules that the computer implements. If you use a different data set, then the checksum might be not 100, but 110. So I hope that makes sense. It's a good question. So what about, right, you can see that, well, an object like a house certainly have even more features, right? So we basically then stack all these features into a long vector, X, in RD, a real space of D dimensions, and we can use the vector to predict the price. Vectors, well, for these problems, more than 2 dimensions is going to be very hard to draw and visualize, like in a straightforward way. So part of the warm-up exercise of this class is to get ourselves used to thinking about vector spaces and even manipulate them, such as differentiate and so on. So that take-home exam 0 will give you some exercise And one practical tip for vector and matrix calculus is that it is an acquired skill. So, it takes a while. If you're not used to it, then just have, for example, the matrix cookbook open and just look it up. After a while, it will become better, and there will be invariably sometimes the equation comes, for example, involving a trace or some quadratic form that's unfamiliar, then look it up. So at this level, I don't think memorizing, for example, the entire vector calculus is super useful. You just invoke it as you need it. Okay. So we talked about regression as a supervised task. Let's talk a little bit about classification. Basically, in here, if we suppose we don't know if something is a house or townhouse, right? So for people who don't know, right, the townhouse are basically houses connected to each other, but houses are mostly detached from each other with land surrounding it, right? In different countries, these things are, like, I guess, are very different, right? So townhouses typically may be smaller and have a smaller land that belongs to it, and so on. So therefore, they split into these classes: triangles, or blue triangles, and orange circles. And you want to learn either, say, a separate line for house price and a separate line for townhouse price, which makes sense. Or maybe you want to learn a best separation between these two classes, so that a new property comes in, you can see which side of the boundary falls, and whether it is a townhouse but it's priced more like a house, or featured more like a house. Maybe that's miscalibrated. So in here, the supervision signal or task Y is then to just do this binary judgment rather than predict the price in real values. So we will talk about classification for quite a bit in different ways: linear classification, neural networks that can be used for both classification and regression, and also kernel methods, and so on, fairly directly. So there can also be unsupervised learning. So suppose we're still in this house versus townhouse realm. You could say that there may be a real estate market, let's say, but these townhouse and house classification don't exist there. You want to discover maybe what are the different types of houses as data objects that's out there, right? Which translates to this unsupervised task. I just have a bunch of dots that visually they might follow, I guess, two curved lines, or maybe even more, right? So you can say, well, let's find out what are the sensible groupings in this data. So note that the clustering, the objective of clustering is decidedly subjective. Meaning, if I care about, I guess, building types, it might be clustered a different way. If I care about, I guess, different stratas of, let's have house buying capacity, maybe I will try and find a group of super fancy houses versus what everybody else buys, and something in between, and so on, right? So if you have taken IML, you would have seen Gaussian mixture models and K-means as methods to find this. And in this class, we're going to take those one level deeper, basically tell you the underlying formulations and a couple of different ways to formulate, for example, GMMs and PCA and so on. And as we said, there might be different sensible groupings of the same data. For clustering, you really have to ask yourself what you're doing with the result. So, so that is unsupervised learning. Let's maybe move beyond this toy example of classifying houses and look at what are some of the learning tasks that's realistic and used in other domains as well. So the emphasis here is there's lots of what we call complex and structured input, right? So for most of this class, we work with the input x as a vector, or the vector passed through some basis function, which is still a vector even if infinite dimensional. But in a lot of real-world tasks, you first have to figure out how to map the input to a vector. For example, if the input is an image, there are many ways to map it to a vector. Just stretch the image as a matrix, line up the different channels, or pass it through some pre-processing to come up with a vector and so on. So image is one common structured input format, which I won't. There will be about 2 or 3 examples in the class, in this entire class that uses images, but you have the computer vision class to cover all of it. Another example that we can illustrate with images is that there are different kind of learning tasks that can be formulated with complex output such as images. For example, the last slide we looked at classification, whether there's a dog in the image. In this slide, we're looking at object localization and detection. So basically, find the boxes that contain the object in question, which is harder or task than the classification task, because we not only need to decide the presence, but we also have to count and localize. So one way to cast this into a classification question is to say come up with candidate boxes that are likely, and then just turn that into binary or multi-class classification. Right? So problem conversion does help. Moving away from computer vision, because a lot of this class is from the MML CV program. I'm sure you have enough computer vision. What about natural language, right? We let's say a sentence, machine translation is a supervised learning problem, which I believe in this statement. Because for natural language sequence, we should translate this whole sequence of tokens, whether it's a sequence of characters, sequence of words, or sequence of, let's say, subword tokens, which is the unit being used in state-of-the-art NLP these days. It's again a structure input, it's a sequence. And then, for example, in machine translation tasks, the output is another sequence, right? So this calls for kind of a different kinds of model, right? So for sequential input, we basically need to have something that takes in more often not the whole sequence at a time, but bits of the sequence at a time, either one token or multiple tokens. We could have, for example, simple classification, binary classification tasks for a particular input sequence, such as sentiment classification. Is there negative feelings in this particular sentence or not? Or we can have, again, this very complex learning task, sequence to sequence, input a sequence, output a sequence in another language. And we say that, for example, machine translation is a supervised learning task because there are plenty of training material that are the same content but written in 2 different languages. Right, so in this class, we cover the basics, but they are not quite enough to directly solve hard computer vision and NLP problems. For NLP is a very exciting area. If you want more of that, go take the doc analysis course in the 2nd semester. And that class is also very practical in the sense that you get to practice using PyTorch and other state-of-the-art machine learning packages to do some of these complex tasks. I have to say, the first time I saw, for example, recurrent neural net processing natural language and spitting out plausible sentences, it is a very surprising and positive experience, because for a thing that as complex as natural language, it can really do the job, which is amazing. Right, there are even more complex tasks, like computers teaching themselves to play chess and Go, all within the same program, and then all performing at the world level. these are some of the later advances in this field, to which I will say that, well, this class gives you a decent and solid foundation to go around and understand some of these more powerful and complex systems. For example, in AlphaGo, one could say that there are essentially two learners. One that predicts future reward, one that predicts what the next step should be. The second one is essentially multi-class classification task. The first one, you could think of it as a regression task. These two put together, plus other bits about gathering data while the system is being trained, makes AlphaGo. Of course, that's very stylized simplification, but it shows you an example about how mastering this basic language could help you understand these complex systems. Right, so since we were talking about reinforcement learning and AlphaGo and so on, one simplified view of them is basically is a learning strategy that does data collection and training in a loop, rather than having basically collection of data that's pre-collected and then try and learn the decision rule or the programming rule from the archive data. So there is lots of grayscale from like supervised learning to reinforcement learning. For example, active learning or bandits is arguably in between them. So take the advanced AI to learn more about these. And then there is also a grayscale between labeled and unlabeled data. For example, this is an example on word embeddings. I don't know how much of you have heard of it. It's been quite widely used in, again, natural language speech, and basically anything related to language these days, starting in 2013. So it uses this concept that some calls self-supervision. It learns the patterns of words by looking at the words that surrounds it. You can call it unsupervised because it's just chewing, let's say, like the Wikipedia data set. It's what people written, but you can also call it supervised or self-supervised because the signal, the training signal of a word is, say, the two words before it and the two words after it. And the outcome of these word embeddings, just from this pile of text written by humans, are essentially what we call one of the like illustrative examples of basically the word analogy task. Right, you can see this in this example, countries and their capital cities lie in lines that parallel to each other. Right, so you could do what's called vector arithmetic in the sense that if I do France subtracting Paris and adding Germany, then we get Berlin, which is quite cool and enables people to do many other things about natural language, such as marking parts of speech or parsing and so on, which is not just cool on its own end. As I said, this is a biased sample of machine learning problems, so I'm going to talk about a few machine learning projects that happens around here at the ANU, starting from those in my lab. So what you're looking at here is what we call SentiCap. It was the first system to train computers to write image captions that has a sentiment, which is either positive, highlighted in green here. So in here, the computer not just can write, it also has a highlighter telling you how positive each word is. The more green it is, more positive. The more red it is, more negative. And you can see that it does a pretty good job in some cases, like a great variety of fresh fruits and vegetables, ugly cat in front of an abandoned building. I think this is very much appropriate, but it does not stand much scrutiny, right? Because Well, here it says, a man in a stupid hat is riding on the back of a crazy horse. That's not correct. It's a grammatically correct sentence, but it does not describe what's in the scene. The person wearing the hat is not riding a horse. And furthermore, it violates common sense, right? A dead man doing a clever trick on a skateboard at the skate park, which is laughing stock. So this work was done around 2015 and 2016. It was part of Alex Matthews' PhD thesis. It was like done by the first generation of recent language models, recurrent neural nets. I was very impressed at what the neural net could do, but obviously it's still not super satisfactory. I will still say the same thing about current language models, because even if you swap this into a transformer or BERT or GPT, it still occasionally makes like common sense mistakes. That's still an open question if some of you are like what really itch to solve that. The second example is again from Alex Matthews' thesis. It's to learning. So in this case, we call this unsupervised learning, in that it does not learn from sentences that are about the same image, but just has a sentiment or not have a sentiment. That was the approach behind the previous one. In this, we just feed the computer a whole bunch of factual descriptions about images, and then we feed the computer a collection of romantic novels. And this is the outcome. I'm not going to talk about how it's done, still with RNNs, but it's able to write descriptive captions about an image, and also story-like captions that tend to have more parallel structure, more of first-person pronoun, and so on. And here's my favorite failure case. It says, I will be in the juicer with a glass of orange juice, as a romantic expression to this. It might be a bit sci-fi like, but again, common sense violation. One more example is again concerning sequences. So myself and my lab have been working on viral videos, or basically the aggregate view count and watch time history of YouTube videos for a long time. And in this particular problem, we look at time series of view counts. In the top, you are seeing two series. One of them is the blue one is for the song Rolling in the Deep. The red one is for the song Someone Like You. As you can see, they sort of correlate in time and have synchronized spikes. These other dots are basically the songs in their neighborhood. They either are recommended from these two videos, or are like recommending these two videos. So there is a mathematical, like neural network model to sort of collectively do forecasting on the whole network of time series in order to do better and reason about their influences, which I think are very interesting. So going beyond, I guess, promoting the work of myself and my lab, here's a sample of things that other people do. Right, for example, the computer vision group in ANU is very strong. One of their projects collects data and trains the computer to learn to assemble IKEA furniture, which is very interesting. If you think about it, it's a vision problem, but it's also a structured, so the output should be a structure of instructions and with the visual cues, but also relations of different parts. It also may have a natural language angle because the instructions need to somewhat in natural language. Although if you read IKEA booklet, it has no words in it, but it's somehow everybody is able to understand that, right? So how to automatically produce an IKEA booklet is a cool research question. Moving on, again, computer vision group. So there's a recent funded grant by Professor Hongdong Li and Xin Yu, who are both working on this topic for a few years with a number of PhD students, basically recognize and translate sign languages. I think this is a very exciting project with lots of potential to benefit humanity, especially the disadvantaged people with hearing deficiencies, right? The problem with sign language is that it is like, but it's not quite like natural language.
Luosing, I think you're muted.
I unmuted. I hope that works now.
I can hear you.
Yep. Thank you. I hope I wasn't muted for too long. Anyway, yeah. So sign language recognition is another cool problem. Moving on. So we're in Australia. Natural resources is a big challenge, and this particular project done by some of my former colleagues at NITA and Data61 is about like using Gaussian processes to do geometric inversion and trying to find where the thermal heat sources are. So in this, I guess in the day of renewable energy, this is obviously a very important question, and machine learning can like make a dent in it, which is nice. If you look around our department or school and generally ANU, there are lots of opportunities to do machine learning in collaboration with another domain. I've already heard from students in this class who are trying to look for projects. They are already working on machine learning for quantum computing and gravitational physics, astronomy, materials, climate change, plants, biology, and so on and so forth. So if you would like to do projects in machine learning, there are plenty of opportunities outside of CS. So do look. I would like to, I guess, trend down this helicopter view of machine learning with a little bit of cautionary note. Some of you, well, this is a cute example of how powerful language models are in the sense that it can not only comprehend language, but also generate pictures that illustrate the sentence, right? A lot of you would have seen GPT in the news. This avocado picture is certainly cute, but what are the downsides, right? When things become really powerful, so technology has had a history of doing both good and bad, right? Just thinking about the development of automobile, people went a long way to develop road regulations. And why is airplane flying so safe? You take an airplane to Sydney without thinking about the risks involved. It's because there's lots of working safety and like assurance and testing that goes along it. For machine learning, it's not quite there yet, right? So machine learning algorithm can appear biased and racist. I'm sure some of you would have read something about it. I would like to highlight a few early examples as essentially cornerstones for these problem domains that are becoming a very active area of research within machine learning and also outside these days. The first example is Latanya Sweeney. She's now a professor in Harvard, I think, but during her PhD, she did an audit of online advertising and found that if you type in a Black person's name and in the US, you get served low quality ads of predatory credit cards and like criminal history checks. But if you type in a white person's name, that's not the case. Yeah, why is that? There's many historical injustices and problematic training data that lies behind it, but there is no simple fix, right? So the second example is Google photo recognition. Mistakenly tag Black people with dark skin as gorillas. As of last year, when I made these slides, Google still haven't fixed the problem. The classification or the class label gorillas as simply don't exist in Google photo tagging. More recently, so this is result from late 2020, people are able to extract training data in large neural networks. Right, to the extent that, so models like GPT-3, I think this is the open source version, you can essentially find memorized usernames and also leaked phone numbers and email addresses from the model, which is really scary if you think about it. So in the digital space, we as humans asked for the rights to be forgotten. If we inadvertently said something that we don't want like the next generation to see, we might delete it tomorrow. But if it made its way into this training data, then it's not going to be deleted. And it's hard to check whether it's deleted. But at least papers like this provides a mechanism to possibly check whether, like, especially if your message and IDs are unique, you can possibly check whether it is indeed in the large model being trained. This opens up a whole suite of technical challenges about how you audit and like large models to make sure that it's doing what we want, using the data that is allowed to use, and deleting the data, forgetting the data that you should forget, right? So I think our tutors were all too modest when I posed the question, potential question as their for their interview as what are the biggest challenges facing machine learning and our area right now? To which I say that like the fairness, accountability, and transparency of machine learning is arguably the largest challenge. So at the ANU, there is also an initiative, Grand Challenge project addressing these concerns. It's called the HMI, Humanizing Machine Intelligence. I'm the current project lead for now. It actually unites computer scientists with a number of people in other disciplines, sociology, political science, and philosophy, to try and all address, and law, to address these questions. As you can imagine, these kind of societal problems in machine learning do not, like, technical solutions are not enough, but it does require a hard core of technical solutions. So for example, fairness and accountability of machine learning is a big research area now. This is one of the paper I just showed was one of the example papers. If you're looking to start a research career, for example, this will be a good place to go to, and there is a lot of research groups active in these areas as well. So that's basically a big picture view of machine learning taxonomy. I'm going to give you some examples about what we don't cover. I said we cover regression and classification and various things. Active learning we don't cover, which is again simplistically in between supervised and reinforcement learning. Transduction we don't cover. Basically, the algorithm somehow allowed to use test data to learn. And also there's semi-supervised learning. And then we are not going to cover estimation with missing variables, like except EM, right? So missing and like latent variables are similar but distinct things. So in if you haven't heard of the expectation maximization algorithm that we covered, we will cover in more depth than IML. We can reason about latent variables. But when data is missing, usually we cannot, like mathematically, we're guaranteed to not be able to invent new information. And we're not going to cover code training. Basically, there are two related data sets or tasks. How can we learn across them? There's a whole area recently called meta learning that sort of addresses this type of problems. And here is a slide that I promised early on the complexity and diversity of the whole field of machine learning. Not to scare you off, but basically we can use contents of this class as a launch pad to understand like all of these diverse concepts and models in machine learning. So, for example, if we think about machine learning as top-level facets, there are topic areas. We're not going to talk about learning theory this semester, I don't think. There was a question about whether we incorporate it maybe next year. And then there are different models. There are different methods that optimize and learn the models. So again, the word model is very overloaded, like precisely in the software sense. In machine learning, it does refer to many different things. In this class, we can think of it as one precise meaning, basically one set of distributions. But when you actually hear people say model in the literature or in the press, they mean all sorts of different things. There's methods on how to learn the models. They can usually be like plug and play with many different, you can learn the same model with many different methods. And problem settings, right, such as what we said about active learning and co-training and so on. And then there are many different application domains. They're just very diverse. I argue no single person has an in-depth view of all of these days. Machine learning is so big, and machine learning conferences are also getting so big. The two main machine learning research venue that happens every year, SML and Europe, are, I think, over 10,000 attendees these days. I think we more or less covered these. I'm not going to repeat. So we will not. This class will not make you an expert in trendy deep learning package. There are other classes where you can acquire these skills, and we'll mainly work with NumPy and build most things from scratch. So in summary, I think this is a great time to learn machine learning because of many reasons, and also very importantly, who knows where the next machine learning revolution or quantum leap will be. And since it hasn't happened, it's a good time to learn it, to be part of it. So it will be like, you will expect significant amount of work on your end. We the lecturer and tutor team are here to help, but do expect to spend time, start early on assessment items, because be prepared in exams. Last year's exam was particularly hard. This year we'll see on how people do on assignments. So that's that. You can, yes, there are many resources that are built around this course, which is most relevant and hopefully saves your time navigating the immense machine learning space. Of course, you are also welcome to use resources on the internet. In the age of online learning, there are so many great, I guess, YouTube lectures on machine learning these days as well. If you want recommendations or want to tell me what you see that's particularly illuminating, I'm very happy to hear about that. So that's pretty much it. Let me stop, or maybe I'll leave the screen as is to see if people have questions. I'm going to be able to write. So I'll leave the screen here to see if you guys have questions. Right, so I'm reading where my team screen is. Can you mention what supervision is again? Asked by Kylie Tan. Right, so yeah, supervision here specifically means that a target variable or the target value for a given input is available. Right. Meanwhile, I think it will take me a while to scroll through this. People can just unmute and ask questions. So if there's no more questions, then I'm glad that, for example, everything about the course is clear. Can think about if you still want to take the class. Okay. Lecture slides are on Piazza, resource page. I'm going to stop the recording and stay on this call for a little longer in case people have questions. Well, thanks, Haiqing. Haiqing is one of our tutors who took the class last year.